Okay, now time for an example about, or more than one example for about the resistances and equivalent resistances of different circuits. So let's consider the following example. In this example, we have four resistances. Two resistances 8 and 4 are connected this way, and we have these two resistances 6 and 3 ohms are connected this way. So we have these four resistances. Find the equivalent resistance between points A and C. We want to find the equivalent resistance between this point and this point. Now, if we look at it, now this is quite simple, but the idea is the following. First, we look at these two. We see these two resistances are connected in series. Why? Because the same current is piercing them. This 6 and 3 ohm resistances are connected on parallel. Why? Because the same potential difference exists among them. How do you know? Well, point B and this point are the same potential. Point C and this point are the same potential. So the potential difference between B and C is the same as the potential difference between these and the same as potential difference between this. So these two are at the same potential. So these two resistances can be represented by their equivalent resistance, which I can calculate using how I calculate the series combination. How I do that? I add them up. These two resistances can be replaced by a single resistance, which is their equivalent resistance. How can I find them? 1 over that equivalent is equal 1 over 6 plus 1 over 3. And this is what I'm saying. Here, this is the equivalent resistance of these two, and this is how I find the equivalent resistance of these two here. And so you get 3 over 6, you flip it, you get 2 ohm. So these two resistances, the 6 and 3, have an equivalent resistance of 2 ohm, and these two together have an equivalent resistance of 12 ohm. Well, a simple observation that worth actually to keep in mind all the time is that when you have two resistances connected on parallel, their equivalent resistance is less than each one of them. When you have two resistances connected on series, their equivalent resistor is larger than each of them. Okay, so keep this in mind. You can prove this generally, but it is also evident from here, in this example, it's quite evident. So this is the equivalent resistance of the whole circuit. Now, the whole circuit reduces to a resistance with 12 ohm connected in series now with another resistance of 2 ohms. So the equivalent resistance of all of this is the single resistance of 14 ohm. Okay, and so the equivalent resistance between point A and C is 14 ohm. It's a single resistance, 14 ohm. The meaning of find the equivalent resistance between this and this, replace all these resistances that exist between A and C with a single resistance and find its value. And this is what we have done in this case. Now he's saying if there is a potential difference between A and C of 42 volts. Now evidently, point A is at higher potential because the current is flowing in this direction. The current flows in the same direction of the electric field from higher potential to lower potential. So the current is flowing in this direction. Okay, so the potential, this point is at higher potential than that point. This might be irrelevant to our calculation, but I always like to emphasize these things and keep reminding you of that. So what is the current in each of these resistances? Current in this, current in this, current in this, and current in this. And what is if the potential between A and C is 42? So between A and C is 42, the potential. Okay. Now, how to start? Well, we first find I, which is the current that passes through the equivalent resistance, but also it is the current passing through these two. Okay? So this I is just what? This potential difference divided by the equivalent resistance of the whole circuit. So it's 32 divided by 14, which is 3 ohms, 3 amperes. So the current this current is 3 amperes. Now this splits into two currents, I1 and I2. I1 passing through the 6 ohm, I2 passing through the 4 ohm. Now the potential difference between the 6 ohm and the 3 ohm is the same. So I1 times 6 equals 3 times I2. okay, because their potential differences are the same. So we want to find now what is this I1 and I2. We know first that I1, we know that this is what I have said. Delta V1 is equal delta V2. So 6 times I1 is equal 3 times I2. This is the first equation that we have. The second equation is from here, or from this, you can get that I2 is equal twice I1. I2 is equal twice I1. So divide by 3, and you get from here I2 is equal twice I1. So this is equation 1. At the same time, you know that the sum of I1 and I2 is 3 ohms, 3 amperes, because this current, I1 and I2, this I splits into I1 and I2. So the sum of these two will make up your I. So their sum is equal to 3 ohms. So I have two equations with two unknowns. Two equations with two unknowns. Okay, I substitute now this for I2 to I1. I solved, I find I1, then resubstitute again and then find I2 again. So as you can see, I2 is 2 amperes, I1 is 1 amperes, and when you add them up, you get the 3 amperes as you expect, of course. Now, what is the potential difference across each resistance? Now, the VBC, the potential difference across this 6 ohm and 3 ohm, after I have found the currents, it's straightforward now. You just multiply each value with the current. So it is either this multiplies by I1 or this 3 ohm multiplied by I2, because they are the same, okay? And you get 6 volts. So therefore, from here to here, the potential is 42 volts. This was given. And if the potential from here to here is 6 volts, then this plus this equals 42. So 42 minus 6 must give you the potential across these two resistances. And so VAB is equal to 36 volts, the potential between A and B. But this is still divided actually among first resistance and the second resistance. But it's not fraud, and you can see that if you add them up, you can get that resistance. Of course, you can also, as was done here, you can also find the potential difference between A and B by just multiplying I by the equivalent resistance of these two, as we have done here. And this is, you get 36. And again, if you add up this plus this, you must get 42. There's an equality sign that is missing here, okay? There's an equality sign. So delta V, this is small a, delta V AB from here to here plus BC should be equal to 42 volts, as I have said, and I have utilized that. Now, one more example. Here, it's about resistances connected in parallel. So we have 3 resistors are connected in parallel, as we have seen. Now here, this is drawn this way on purpose. So as you can see, although this 3 ohm resistance is not drawn parallel to the 6 and 9 ohm resistances, but it is still on parallel, connected on parallel with these other 2 resistances. Why is this? Because, as I mentioned, in circuits, resistances are considered to be connected on parallel, not when they are drawn parallel to each other, not necessarily when they are drawn parallel to each other. Actually, it is not, has nothing to do with being drawn parallel to each other. It is when the potential difference between them is the same. So the potential difference between this point and this point, and this point is 0. This point and this point and this point are the same potential. This point and this point, this point and this point are the same potential. Okay? So the potential difference between this point and this point and this point and this point are the same. Because this point also is at the same potential at this point. The potential difference between this and this is the same as the potential difference between this and this, is the same as the potential difference between this point and this point, or this point and this point. they are all, the potential difference between them are the same, because their ends, the ends of the two, all the three resistances are at the same potential. This is the major criteria. Their ends are at the same potential. Okay, so this end of the end of this end and this end and this end are the same potential. This end and this end and this end are at the same potential. So the potential difference between them is the same. Okay, so these are connected on series, on parallel. I'm sorry. So they are connected and shown in parallel. And the potential difference of 18 volts is maintained between point A and B. So the potential difference from A and B, which will be at the same time the potential difference across each resistor, because there are no circuit elements between this point and this point, or this point and this point. So this potential difference is just the potential difference across the resistances. Calculate the equivalent resistance of the circuit. Well, this is a simple calculation. You have three resistances calculated or connected in parallel. So the expression for their equivalent resistance is very simple. You just apply the formula. 1 over 3 plus 1 over 6, 1 over 9 equals 1 over R equivalent. And so R equivalent in this case will be 18 over 11. Sorry. Yeah, you make a common denominator, and you get this. There should be an 11 here, okay? Because you make a common denominator, which is 18, and there is a missing 1 here. So this 11 over 18. So R equivalent is 18 over 11. You flip it, and you get 1.64. So this is the equivalent resistance of the circuit. Now we want to find the current in each circuit. It's just similar to the previous exercise. Okay, but here the potential difference is easier. The potential difference is known across them. So I know the potential difference across each one of them. I know the resistance of each one of them, and I find the current. So I1 is just delta V, which is 18 divided by 3. The other one is 18 divided by 6. The other is 18 divided by 9. So these are the currents found piercing each of these resistances. Now, what is the current delivered to each resistor, and what is the total power delivered to the combination of resistances? Well, the power delivered to a load resistance is I square multiplied by the value of that resistance. So it's straightforward calculation. Since we know the current through each one, we know the values, we find that through R1, the current through R1, the 3 ohm, is just 100 watt. The current through the 6 ohm is 54 watt, and the current through the 9 ohm is 36 watt. Okay, note this is the smallest value, smallest resistance, but it drags the highest power. Why? Because when it's smallest, and because they are connected in parallel, it has the highest current. Okay, and the power goes like the square of the current. So even if the R is small, I is large, and this is what happens. So this is a general result actually for resistors compared and connected in parallel. The power, if they are the same potential, when they are the same potential, the power through the smaller resistor is always higher. The power, thermal power dissipated in that resistor is always higher. Now, if you add these up together, it will be 198 watt, and if you find the total power delivered to their equivalent resistance, it's just delta V square over R equivalent. How does this? Delta V, you just find I is the delta V over R, okay, and you multiply it by R. Square it and multiply it by R, so you get this expression, and you get this. So this comes from where? Delta V over R equivalent is current. This is squared. It becomes delta V squared over R squared equivalent. Multiply by R equivalent. This cancels. You are left with R equivalent in the denominator. And if you do this, then this is the result, which is exactly the same as this result. So if they are all replaced by equivalent resistance, the power delivered to the equivalent resistance is the same as the sum of the power delivered to each resistor individually, as we expect. Now, there is an interesting point here again, just for you to think about it. What if the circuit shown in the figure was shown this way? Okay, the circuit looked this way, not this way. How will our calculation change? So the electromotive force now is here in the middle. It is not in the on the side as it's happening here. What do you think? Think it over.